All right. So we completed discussion on so-called linear data structures, which is arrays and linked lists. Now let's go into non-linear data structures, starting from trees. And the job of, my job in this set of lectures is going to be to make you imagine trees upside down, right? That is, the root is at the top and the leaves are at the bottom, right? So let's get started. Um, so trees get used in multiple applications, or at least we encounter them at multiple places. Before I show you what applications use trees, um, may I ask in what context you have encountered trees? Right? Those of you who know what trees are. The question is that have you encountered trees anywhere? Okay. Salman says he can view a process tree as a tree. That's a correct analogy. So you have a parent process which can fork child processes, and child processes can themselves fork further child processes or grandchildren processes. So those form some sort of a tree, right? Then trie is a tree, that is correct, Shania, which is a different data structure which is used primarily for searching for, let's say, characters, typically more like a dictionary. But that's a little different data structure which we are unfortunately not covering because we have limited time, but that's a very interesting data structure. Vikash says decision trees, right? So many of you who would have studied some sort of machine learning AI, you would have come across this decision trees where, let's say, there are large number of customers. You want to figure out, okay, age group is within this and the salary is within this, then this person is likely to buy a certain product and so on. So, right. So this can be done at different levels of these decisions, that, okay, what is the age group, what is the salary range, etc. So at every level is one decision. Good. Then file directory. That's a very interesting observation. Abhishek says you have a directory. Inside that there could be further directories and files. Within direct subdirectories there could be further subdirectories and so on. That can form a tree, assuming that there are no links involved in this. Aniruddha says syntax tree in compiling, right? So you have some sort of a program given, and that can be modeled using a tree. Not only expressions like we saw, A hash B at C, right? So that was one syntax tree that I showed. But even otherwise, for example, even the loops and functions, etc., can be modeled using some sort of a tree. That is called a syntax tree in compilation. Abhishek says phylogeny tree. That is also another nice example. Nikhil says recursion processes. This I am not sure because recursion essentially forms a loop, and one of the properties of the trees is going to be that there are going to be no loops in it. Nikhil says f of n minus 1 plus f of n minus 2. Oh, I see. That way. Oh, I see. Okay, I understand what you are saying. Yes, so if you have, for example, factorial function or Fibonacci number sequence or some sort of such a mechanism, then you can model this as whatever is being computed for n, that is being computed from n minus 1, n minus 2, etc. Right? So that seems to be another good example. But in general, we can also see that non-recursive processes, I mean, the way functions get called, that can also be viewed as a tree, right? It's actually called as a call graph. If you do not have recursion, then it can be also called as a call tree. So that seems to be another good example. So that's good. I'm happy that you have encountered trees in some form and you are able to visualize those, right? So those of you who are not aware of what trees are, don't worry, that's what we are going to study now, right? I'm just going to give you some of the examples, and some examples will match with whatever suggestions our friends have given. So manager-employee relation can be a nice tree-like structure inside companies. And an employee can be a manager of somebody else, and that is where this relationship comes into picture. In a similar manner, you can think about the our ancestry, right? So great grandfather, then or great grandparents, then grandparents, then parents, yourself, and later your kids, etc. So all of these are going to be forming some sort of a let's say ancestry tree, right? So that is also another way in which you can visualize. Maps at different levels you can zoom in, right? So at different levels you can see the picture of an area, and then you can zoom into it to see finer details, etc. So these different levels can be viewed as different let's say nodes inside a tree. Then the computation where main is calling some function and let's say fn as well as app : bars, that forms a tree as we were discussing. Expressions form a tree as we discussed. Well, there could be a hierarchy which might be a little unnatural to model, which might not be explicitly occurring but implicitly. For example, there could be a universe, within that there are multiple galaxies, within that there are multiple stars, and so on, right? So all of this can also be formed as some sort of a hierarchy which can be nicely represented as trees. Let's come to the nomenclature. For now, we'll view this tree upside down. So what are the things that we know about trees? General trees that you see around. I mean, around meaning in real life. So what are the parts of a tree? Let me ask that. I know this is not the science class from your earlier days, but okay, let's look at this. So we have these branches, then we have root, then we have root leaf, then we have branch, root, leaves, branch. Okay, anything other than root, leaves, branches? Stem, good. Roots, good. That is what I wanted to check. That some of us who are already aware of trees will probably give a very biased answer that okay, there is root, there is leaf, there is branch, etc. But then there are stems, fruits, flowers, good. So all of this happens, and somebody might, okay, seeds, nice. All of these are good answers, and we are going to I'm just going to list some of these. However, when we are dealing with the trees inside the computer or the trees as data structures, we are going to not have some of these and have some of these. So stems and branches will put together and we'll say that those are called as edges. And root is a special node. So the trees are formed using nodes and edges, right? So we'll not have fruits, we'll not have flowers. But then I should also mention that some of the advanced algorithms, they are really interestingly named after some of the fruits and flowers. But anyway, that's not currently our concern. So let's define it formally. So we say that a tree is a collection of nodes, right? Each node is essentially one part of the tree. It could be empty. That means that the tree may not have any nodes. That is the base case. Otherwise, it consists of a root node, which is the first node that you will encounter in some sense, right? Because the tree grows from the root, and that root is connected to 0 or more child nodes, right? So the root kind of emanates from itself, the seed grows, and then it converts it into multiple nodes, or multiple nodes get formed, which are also called as child nodes. And each of the child nodes can form a tree in itself, because we said that tree could be empty as well, or it could have a root, right? So each of the nodes could be the root of its own subtree. And this forms a recursive definition of a tree. And that's also one of the important reasons that many of the algorithms that we are going to study are going to be recursive when it comes to trees. Similar to the way we have seen that the arrays as well as lists could be defined in a recursive manner. So this turns out to be a tree, right? And then if I just reorder some of the edges, then the same tree can be viewed like this, right? So the visualization might be differing, but we do have both of these are turning out to be trees. And since we show the root at the top, that is the root, and these are the children of the root, that is in some sense first level, then there is second level, and so on. And these second level nodes in this case do not have any children, and therefore these are also called as leaves, right? So there are roots, then there are internal nodes, and then there are leaves. I'm going to define those. And since it is usually shown in this manner that the root is at the top, and therefore we view trees upside down, as I was mentioning. I can have an alternative definition which is not recursive. For example, a tree is a collection of nodes and directed edges, right? So what do you mean by directed edges? Sometimes the relationship between two nodes might not be directed, and I'll come to that in a while. But in this case, we say that there is a parent-child relationship between two nodes whenever they are connected by an edge, right? So there is a parent-child relationship here, similarly here, but there is no parent-child relationship in this case, right? So these are directed edges such that each node except one has a single parent, right? The node without a parent node is the root, right? So this is a little loose definition. This is not the proper definition, because we also need to worry about the connectivity, right? But I think that will get guaranteed because only one node is root. Okay, so I think this should be okay. So this collection of nodes where each node except the root has a single parent, that seems to be an interesting observation. So I would recommend that those of you who have some thoughts about this particular definition, try out to draw a data structure such that it doesn't form a tree, right? So it doesn't form a tree, but you try to follow that each node has a single parent, and see if you get something other than trees. So if yeah, so I'll leave it at that. One question that comes up, okay, there are some questions here. What is the difference between two diagrams? Their node addresses are different, Mayank is asking. So no, it's actually the same, only the visualization is different. The node addresses are also the same. In fact, the two trees are equivalent. I mean, assuming that it's the same tree, right? So you can have two different trees which can be viewed in two different ways. But that was just one way of specifying that the edges might cross each other and so on while visualizing. But when it comes to trees, you will be able to draw those similar to the right-hand side tree where there is no overlap across edges. Murari says, especially there can be multiple root. There can be multiple roots in the tree. No, there cannot be multiple roots in it. So since there is only one node which is not having any parents, there is only one root in the tree. And
yes, sir, I was thinking there could be intersection between two trees and two roots could be possible, but yeah, I think it's wrong.
Yeah, sure. But there is something called as so if you have actually multiple roots in your data structure which are connected to, in that case there is going to be a collection of trees in your data structure. Those are called as, can somebody guess what that data structure will be called as? Yeah, so as some of you have rightly pointed out, those are called as forests. And these names are okay. That is not called as a graph. I mean, graph is a very generic term. So each tree is a graph, each linked list is a graph. But graphs will have something more other than so this particular constraint that the node should have a single parent, this will go away. Similarly, because of that there can't be any cycles in the graph in this tree, right? Whereas in the graph those will also be allowed. So these collection of trees are called as essentially forests, as rightly named. Okay, so now let me ask you this question, that we said that It's a, so there are two things we want to discuss. One is about directed, undirected, and second one is about except one has except the root, everybody has a single parent. If I add one parent to this root, right? I don't increase the number of nodes. I just add one edge into this tree, right? Such that the root now has a parent. What will happen? So I hope the question is clear. Okay, Suryanarayan says still a tree. So I'll repeat the question. The number of nodes remain fixed, but I am increasing one edge such that the root now has a parent. Rishabh says parent will become root. Okay. Rohit says the parent becomes like a root. Okay. Any other suggestions? Okay. Aniruddha says it won't be a tree. Shania says not a tree since number of nodes is fixed. There might be a cycle. Okay. Abhishek says without root, how we can say it is a tree? Sure. Okay, I'll wait for a few more seconds in case somebody wants to say something more. All right. So let's understand what is happening, right? So we said that the number of nodes remains same, right? Let's take this particular example that is there on the screen. There are 7 nodes in this, and there is one root currently. I'm going to allow you to add one edge such that the root node has a parent, which means that there is a directed edge from one of the 6 nodes to the root now. As soon as you add that edge, right, there is no node which is having 0 parents. Everybody has 0 parent, and therefore it cannot technically be called as a tree, right? Suryanarayan also agrees with that. So it won't be a tree because there is no node having a parent, right? So you can there is no starting point, so to say. More importantly, as Shania says, the whichever node you choose, whichever of these 6 nodes you choose, you are going to have a cycle created, right? So if you choose, for example, this node as the parent, I am going to add this edge, right? From that to, please pardon my drawing skills or lack of it. But there is an edge from this bottom node to the root, the original root. And as soon as that happens, there is a cycle because there is already this path between these two, right? And therefore this is creating a cycle. So, and you can choose any node and you can choose any kind of tree and you can add an edge, and it is guaranteed that it will create a cycle. Can somebody tell me small logic why adding one simple edge, directed edge, to the original tree will create a cycle? Okay, Rohit says, yeah, won't be a tree. Earlier thought a new node is being added as a parent to a root. Okay, sure. Mayank says umbrella kind of structure. I see. You mean the way it is drawn? Sure. Yeah, my question now is that can you think of a logical answer that you are given a tree? If you add one edge, it will always create a cycle. Can you give one sorry, if the root node is added a parent, then it will always create a cycle. Can there be an argument to that? From any node, there is a path from the root. So when we now join it to the root, there is a path from the root to the root via that. Very good. So that's a logical reason why it will create a cycle, right? Because each node in this tree is originally reachable from the root. Each node in this tree is originally reachable from the root. That means there exists a path from root to every node in this tree. Now when you add an edge from any of these nodes back to the root, root can reach itself via this path, and therefore there is a cycle that is getting created. That doesn't mean that a cycle will get created when you add any edge, right? So a cycle will not be created all the time. Let me just remove this. For example, I can add this edge. That is not going to create a cycle, right? This is called as actually a DAG, directed acyclic graph. This is not a tree, it's a specialized form of a graph, right? Okay, so that is one thing which I wanted to discuss. The second one is about the directed and undirected edges. In trees, we are going to have directed edges unless specified otherwise, but there exist some relationships where the kind of relation is symmetric, right? So in some sense, this is asymmetric relationship. The parent and the child relationship is asymmetric. You cannot be a parent of your own father, right? So in that way. So um, but some relationships, for example, let's say brother-brother relationship or sister-sister relationship is going to be symmetric. In that case, if you want to represent this relationship in data structures, then undirected edges will come into picture. So Salman says, isn't there a cycle in it? Where is the cycle? So according to the new edge that I added, no, there doesn't seem to be any cycle. Can you?
Sir, can't we form a cycle of 4 nodes using that red arrow?
Oh, no. Okay. This is okay. I understand what you are saying. So since this is directed graph, therefore the cycle has to follow the direction of the edges. If you convert it into undirected graph, undirected tree, then there is going to be a cycle. That is what Salman is saying. So if this is 1, this is 2, this is 3, and this is 4. Then 1, 2, 3, 4 will create a cycle if you ignore the direction of the arrows. But if you consider direction of the arrows, there is no cycle. So you are right. If this tree would have been with symmetric edges, that is undirected edges, then it would have formed a cycle as soon as you add the one edge beyond the tree. That is correct. And that edge could be anywhere. It need not be only with the root. It could be anywhere. Right? So that's a good observation. Abhishek says arrow is not in both directions, so it is not correct. Yes. Okay, so let's move ahead from here. So there is some nomenclature which we need to follow when we are dealing with tree as a data structure. I'll just mention that because it will become easier for us to talk about it. So I'm going to color code the nodes, and a root has no parent that we know of. Leaves have no children, which are specified as blue at the bottom of this tree. Non-leaves are internal nodes, including the root node. All of these are called as internal nodes, right? Okay. Now the question is, I want you to draw trees having certain number of nodes. Please try that in your copies. I'll get you started. I'll draw the empty tree. That's the most difficult tree to draw. So I'm going to draw that. So empty tree is nothing. It doesn't have any nodes, right? Tree with one node also should be okay. Oops, sorry. So I would like you to draw tree with 2 nodes and trees with 3 nodes. There might be multiple. So assuming that some of you have tried it, so the trees will look something like this, right? And are there any questions so far? And I will also mention that since we are talking about directed edges, that should also give you a hint that our directed edges were there in linked lists also, and therefore we'll be able to use pointers to implement these data structures, and that also indicates that pointers are one or directed kind of what you say, directed entities, right? These are not undirected. Okay, good. So the observation is one is that each node is reachable from the root, right? So this should be understood very clearly, and therefore there is some sort of connectivity across all the nodes, right? And that means that if I just give you the root, then you don't need to worry about the rest of it. Rest of it is going to be reachable from the root, and therefore it can be accessed. Similar to that, I don't need to keep track of each node separately. I just keep track in a linked list. I just keep track of the head, and that gives me the complete list. Okay. Each node can be viewed as the root of its own unique subtree, right? So for example, this itself is a subtree. This is another subtree. This is another subtree, and this one is another subtree, right? So all of these are different subtrees according to our definition of trees. So that is another definition of a subtree, right? Even the child of the leaf nodes or the children of the leaf nodes can be called as subtrees, just that those trees are empty. Okay. Any other any questions so far?
Each node can be viewed as the root, like except for the leaves, right?
Even the leaf can be viewed as a root,
Okay,
which
yeah,
has a
see, with
single.
single node, right?
Yes,
Root
correct.
with single node. Okay.
Yeah. Any other concerns, questions? Okay, so we'll move ahead. So there are certain properties. Some of these we have already identified. For example, each node is reachable from the root, right? So that is one property. But there are some quantitative properties also that we need to identify. There is another property that we identified, that if you add a parent to the root without adding any new nodes, then that is going to create a directed cycle. Similarly, other thing we identified was if you add any edge to the tree, then it does not remain a tree. So that was so that is another property, right? So let's say that a tree has 6 nodes, right? So what is the minimum number of edges in this tree, right? To make this set of nodes into a tree, how many minimum number of edges do you require? Please think about it, and then you can also type it in the chat. Okay. Okay, so all of you seem to have thought about that we require 5 edges. Essentially, if you have n nodes, n minus 1 edges to form a tree. Anybody wants to say any other number? Can you connect 6 nodes with 4 edges, for example? Okay, so that doesn't seem possible. If you have to form a tree, you will have to have n minus 1 edges, and therefore minimum number of edges in the tree is going to be n minus 1, right? What is the maximum number of edges you can add such that the collection of these nodes continues to remain a tree? Okay, so all of you are saying that this minimum and the maximum is going to be the same, and therefore this is in some sense saying that this is a tight data structure, right? You neither can add any edge nor can you remove any edge, right? So that answer is also correct. So that is n minus 1, which means that if I give you n nodes, that tree is going to contain n minus 1 edges, right? Directed edges, right? One question which I'll mention, but I'll probably leave you with that: how many undirected paths exist between two nodes, right? So if you take any tree that is going to have some sort of a path, if you ignore the direction, right? The root has directed path to every node, but not every node has directed path to each other unless they have ancestor descendant relationship. So if you take for example two children of a root, then those are going to have a path between them going from the root, right? Undirected path, right? So after ignoring the arrows. So how many undirected paths exist between two nodes? Can somebody think about it? NC2. Okay. So the question is that I'm giving you two nodes, N1 and N2 in the tree, right? In how many ways you can go from N1 to N2 if you ignore the direction of the arrows? Charan says one unique way.
Sir,
Yeah, Aniruddha.
do we also count paths that make sort of like useless moves, like go front and come back sort of moves?
Oh, I see. Thought about it that way. Yeah, maybe I should have written simple paths, but yeah, I didn't think about it that way. So yeah, if we avoid that, then what is the answer?
So if you avoid that, it will be a unique way.
I see. I see. I see. I understand. So I understand what Murari is suggesting. A to B and B to A are different. Then it is 2 times NC2. I see. Salman says 1. Rohit says 1. Okay. Okay. So maybe what I'll do is I'll go back to this slide and show you this tree. So if I take this as 1 and this as 2, right? Maybe I'll ask Mayank and Murari to suggest why there would be 2 NC2 paths or NC2 paths. You have given 2 nodes, right? Oh, you are saying across all the nodes. Oh, I see. I see. Okay, I got that. I see. Okay, I understand your answer now. So you have taken all pairs of nodes, right? And that is the reason why you have given that answer. So the undirected path is going to be between given two nodes N1 and N2. It is always going to be a unique path, right? So that is another property which is satisfied. And you can try drawing different kinds of trees, right? So in this case, for example, this is a tree. Oops. This is a tree, and this is also a tree with the same number of nodes, just that the number of edges is different. Number of edges will remain the same. The way they are connected is going to be different. So this actually turns out to be a simple path, the first one. So it can actually be represented as a linked list, whereas the second one is going to be kind of one level or two levels of trees. A little bit of more nomenclature before we jump into some algorithms related to traversals. One thing is about the siblings, that is also borrowed from our ancestry, that we have brothers and sisters, and to be gender neutral, sibling is one good name. So siblings are where the parent is the same, right? So two nodes are siblings if their parent is the same. And since there is unique parent, we'll say that it's a parent rather than parents. So maximum number of siblings a node may have in an n node tree. Any suggestions on that? Salman says n-1, Shreya says n-1, Surya says n-1, Shania n-1, Murari says n-1. Anybody wants to give a different answer? Okay, I'll take Andrea's answer, n-2, right? Because you will not say that a node is its own sibling, typically, right? So ignoring that, it is going to be n-2. And then there are like grandparents and grandchildren. All of this relationship is also going to be existing in a tree, which we can talk about. In general, we can talk about ancestor-descendant relationship. And whenever it comes to ancestor-descendant, that is, what does that mean? When do we say that one node is an ancestor of another node? Okay, the question is, when do we say that a particular node is an ancestor of another node? Aniruddha says there is a path from first node to the second one in the directed edge case, right? Pavan says when you can reach the second node traveling more than one edge. Okay. Sai Charan says if you can go from the ancestor to the other node. Shania says without involving root. Okay, so I think there are multiple things we'll have to talk about. Okay, so is parent an ancestor of a child? Yes. Okay. So then I think the path length can be 1 as well. Andrea says when there exists a single path from that node to the node under consideration. Okay, sure. Right. So ancestors is essentially going to be from one node N1 to another node N2, as long as there exists a path from N1 to N2. Now, depending upon the context you might want, or depending upon what your application is or what relationship you are encoding into the data structure, you might want to define ancestor relationship to be reflexive or not. Reflexive meaning whether the node is its own ancestor or not. This can differ in general across applications, because for example, if I am talking about let's say one particular actually the manager employee relationship, then that relationship is not reflexive, in the sense that a person cannot be its own manager. However, if I'm trying to talk about, let's say, function calls, right? Can a function call itself? Yes, it can call itself, and therefore we'll say that we'll be able to model this in this case where the ancestor can be itself, right? So depending upon that definition, the meaning of ancestor might differ, but definitely parents, grandparents, all of them are included in the ancestors, right? As long as they have a path to this particular node. Without involving root, this is a little tricky because the root itself might be an ancestor, and therefore it might be part of the path within in this path. Right? Okay. This particular ancestor-descendant relationship, as we talked about a path. Path is just a sequence of consecutive edges, right? Which are where the nodes are essentially going to be target of the previous edge and source of the next edge. For example, this is a path. Right? So we typically model these using the nodes. So if these are numbered as 1, 2, 3, 4, I'll say that 1, 2, 3, 4 forms a path. The length of the path, again, that can differ in terms of the definition. Sometimes it is defined in terms of number of edges. Sometimes I have seen it defined in terms of the number of nodes that you visit in this path. So what we'll do is we'll define it as path length in terms of number of edges, or path length in terms of number of nodes, right? So that way it will become unambiguous. So the length of the path from root to the child node for the central leaf node is going to be of edge length 3 and number of nodes is going to be 4. Right? So that is the length of the path. And then height and depth are two other definitions which get often used. Height is from the bottom, that is from the leaves, whereas the depth is from the top. Depth typically starts at 0, which means that the root is assumed to be at 0, but there exists some literature where root is considered to be at level 1 and so on. Again, we'll define it in clear terms that whether the root is at level 0 or not. The height, I said level, I should say depth. Because level is a little ambiguous. Level can be used in either way. It could be called as height, that is bottom to top, or depth from top to bottom. Height typically starts from the leaf, but then the leaves, not all leaves are at the same level. Right? When we talk about a height, not all the leaves are at the same level. So which height we should be talking about? For example, if I say that this is height 2, this is height 2, this node is at height 2, that is with respect to this is 1 and this is 2, right? But if I take this height, then it is going to be at height 3. So which one should I pick? So to make sure that there is uniformity with respect to the height, all the leaves are assumed to be at the same level, at the ground level, right? So this tree I'll have to draw such that this node is going to have a node here, and that is going to have a leaf here. And in that case, I'll be able to say that this particular node is at level 2, and then this is at level 1. Root that way has different length paths, right? So what is its height? It is at height 3 also, it is at height 4 also. So depending upon when you are defining complexity, typically we'll have to take the maximum height it is at, so that we can talk about worst cases. But again, that needs to be distinguished with respect to whether it is the minimum height from the leaf or the maximum height from the leaf. Any questions on this nomenclature? Anything which is unclear? Don't worry. I mean, you don't need to remember all these terms. As we go along with the discussion, we'll recall these. But those properties you need to think about, right? The way we discussed earlier. Right? So some of the exercises which we'll do, or maybe I'll just discuss quickly, but you should think about these offline, is that given a pointer to a node in an employee tree, right? So the employee manager relationship, I would like to list all its direct and indirect subordinates. We have not yet defined a tree data structure as such in program, which we'll do soon. But assuming that you have this pointer and then there is list of employees given some way, whom that particular manager kind of coordinates with, can you print all the direct and indirect subordinates of that particular manager? Also, it might be interesting. Mayank says height can be equal to depth. It's possible. I mean, the depth of a particular node can be the same as its height. That is possible. Somewhere in the middle, that can happen. Or if you have, for example, if you consider a tree with one node only, then the height and the depth will turn out to be the same, assuming that you are starting from one.
Sir, but the doubt is height is always starting from 1, but the depth can't be, it may be from 1 or maybe from 0.
Yeah, those problems exist in literature, and that way, whenever we define this height or depth, we will specify explicitly whether the height starts from 1 or 0, and similarly for depth. Right?
Okay, sir.
Yeah, and in general, the height and depth are different. Okay, good. So so the first exercise that I am listing here, while it can be done nicely in an iterative manner, it's probably going to be more natural, and we'll see that naturality coming into picture more and more as we talk about trees, to model this in a recursive manner. So it might be easier for you to write the code. Even if you write a pseudocode, it should be all right, but do try that out. Now, instead of the pointer to that node, if I tell you the name of the employee, name of the manager, and I want you to give all the names of the direct and indirect subordinates. Direct meaning children, immediate children, indirect meaning grandchildren, etc. If I give you two nodes, can you find out the distance between two nodes in terms of the path length, which could be number of nodes or number of edges, in an undirected sense, right? So there exists a unique path, undirected path, that's what we said. Now can you do it? Can you find that out? You can start small, and by saying that I'm going to give you only the two nodes which have ancestor-descendant relationship, and that will make sure that there is a directed path between the two nodes. Right? So that you can then generalize to an undirected case. How about the tree diameter? That is, you are given a tree, and then you want to find out the maximum distance with which any two nodes are going to be separated. The NC2 pairs that we talked about, that Mayank and who else was talking about that? Maybe Murari was talking about that. Yeah, so they were talking about the NC2 pairs. Within that, whatever is the maximum distance, that is called as a tree diameter. Can you find that out? Can you write a code corresponding to that? These are all going to be little challenging as we go down in this exercise list. Given an infix expression as a tree, right? So we have seen an infix expression as a tree. Given that tree, can you convert it into postfix? Yet you are not given it as a string, you are given it as a tree. Can you mirror a tree? Mirror a tree meaning there is a mirror beside the tree, and now you want to make, let's say, a particular node has children E1, E2, E3. Then the mirror should have that node, should have the children as E3, E2, E1. And that should be followed at every level. So that is called as mirror image of the tree in a vertical manner. So that can you do. And then the last one is similar to the distance thing, where given P and Q, find out if there exists a path between these two from P to Q. Right? So this is not easy because you will have to probably traverse through all possible paths. But this is a good exercise to get started, and I would recommend you try these out, and if there are any questions, feel free to discuss either in the class or on the group. I see that the group activity is a little low, only the assignment related, it's a one-way communication, it's a directed path, right? So you guys are not discussing anything on the group, so I request some of you to try that out also. Okay, we'll stop here, and those who have questions can stay back, those who have classes can move.
So that one place you are saying that. Am I audible?
Yeah, go ahead.
At one place you are saying that there is n minus 2 siblings. That I was unable to understand.
Oh, I see. So siblings are essentially nodes having the same parent, right? So if you leave out the parent and yourself, then there will be n minus 2,
Okay, sir.
right? Aniruddha says, can you explain the mirror tree again? So you are given this, okay, let me name this nodes, right? So there is a root node has E1, E2, E3, and then E1 has, let's say, x1, x2, x3, E2 has, let's say, x4, and then E3 has x5, x6, right? So the mirror image of the tree should look like you form a new tree such that it will have the root same as the root, and then its children are going to be in the reverse order. So E3, E2, E1. E3's children are going to be x6, x5. Then E2's children is going to be x4, and E1's children are going to be x3, x2, x1.
So one doubt regarding mirror is, sir, where mirror like be placed after visualizing, like top of the root or besides the like root?
You mean of the original tree?
Yes, sir. In original tree, we have to take the mirror image, right, to create a new one. Like, and the when we have to take a mirror image, like the where like mirror is actually placed in which
I see.
direction, like
I see.
above the root or
Yeah.
just beside.
Yeah, so we'll say that you are going to create a different tree, which is going to be the mirror image of the first tree. So create a different tree. I think that will be easier.
But still, sir, like mirror image is okay, fine. But mirror in at which place? Like there is one place, not top of the root, right, sir? And one is like just besides the root, beside means like the left or right of the like line. Means like the edges, like the path. Like there is two way to place the mirror.
Oh, I see. I see. Okay. The mirror is placed vertically,
Oh, okay, sir. Okay, sir.
right? Yeah. Okay. Abhishek, sir, in this right-hand side child will go to the left-hand side child. Yes, that is correct. But there could be multiple children. But yeah, you are right. Anybody still has any questions on this mirror image of the tree? Okay. Any other questions? Okay, Aniruddha says order of children has a significance in trees. Well, I would say it depends upon the application. Many times there is no ordering, but the way you store it in a data structure typically has an ordering. For example, if we talk about expressions a minus b, and if I represent that using a tree, then definitely the ordering of the children matter. But in some other cases, for example, employee manager relationship, that order doesn't matter. So it definitely depends upon the application. But yeah, in this case, we'll assume that that order is important. One says bottom right, bottom and bottom left directions are distinguishable in a tree. Yes, I think it is also related to Aniruddha's question that whether you are able to have some ordering amongst the tree. In this case, we will assume it to be that way, but not always that is the case. In this particular application, as well as in all our implementations, there is going to be a distinction with respect to the ordering. Right? The ordering needs to be enforced in some way, so that we'll follow. So we'll be able to distinguish these different parts. Yes. All right. So if there are no further questions, we'll stop here.
So just one question.
Sorry,
if
yeah,
we
go ahead.
instead of having directed tree, if we have undirected tree, that is having both pointers up and down, will it be somehow helpful while we are traversing or recursively traversing the tree, like going back to the root node or the parent node?
Yes, so that's a good question. The question is that if we follow undirected path rather than directed path, will that help us in traversing the tree? For example, we'll be able to go back from a child to its parent. Yes, and if your application does demand that, you should have that form of a tree, undirected nature. Alternatively, it's not necessary that it should be always represented as a one-way direction in your data structure. You need not say that it is a tree. I'm just representing it as a graph where there are both way edges I'm storing. So that is also okay. That is not a problem. And yes, it does help. In some applications, some small set of applications, you can actually store a tree in where the edges are in opposite direction. That is, only the child is referring to the parent, and you don't have any way to go from parent, because your application actually starts from some node, and then you want to find out who the root node is, right? So in some sense, you are finding the CEO of a company given any employee. So in those applications, you will store the tree in a reverse order. In fact, it will not be a tree, although it will look like that, because the root node will have multiple parents. So, but yeah, you can call that as a reverse tree. Anish says, are graphs a part of our portions too, or is it only for the CS section? Graphs is definitely our concern as well. It's just that uh, depending upon the amount of time we have, we would like to cover that. Right? So graphs we are going to study. Any other concerns? Abhishek says, when we will be studying sorting. Yes, that is still pending. I'll do that sometime. So there are a few algorithms that we study usually in sorting, and some algorithms are not often taught as such, and but those are actually performing quite well in practice. And I would like to highlight that practical aspect in the sorting discussion, where we actually code those up and run on the same input and see how the comparative behavior of different algorithms is. That way you will get a clear picture, right? So we know about, for example, merge sort, quick sort, etc. But there are other sorts which might turn out to be very useful. So that is what I wanted to cover. But yeah, I'll do that. I haven't decided when exactly, but I'll do that. Don't worry. If you guys think that I'm going a little slow, please give me that feedback. Or if you think that I'm going fast or the pace is okay, please let me know, so that I can, because I know that initially it does take some time to sink in some of the concepts, but we might be able to go faster now that you are well aware of the pointers and data structures. Okay, so we'll stop here.